All right, well today we have a homework assignment due on stacks and queues, and also we have a paper coming up. So before we do anything else, let's see if we have any questions about, first of all, what about the homework, what about the stacks and queues? Oh, by the way, that's another tip. You know that whenever you use the adapter pattern with the list implementation of the stack and the queue, those lists already have built into them the streaming, so you don't have to redo that. You just use that.
Use their streaming.
Use their No questions about the paper? LaTeX tips? Anything? Oh yeah, that's a good point. Actually, this comes up a lot. Look, you guys. So if you do one of the graphs, and like one of them has, it's way really big, and then all the other ones are way down here. Did you notice that happened on one of your graphs? Well, look, what should you do? How should you make this better for the reader of your paper?
Separate each graph?
Well, I think all you have to do is, I mean, you can show this to see how it's really big. I mean, how this is really big compared to this. But then I think what I would do is I would do another graph, another plot, where you leave this one off. Then these will expand up, and you'll be able to see them. See, so for the courtesy to the reader, you see, that would be the way to solve that problem, that issue when you're writing your paper. Okay? So everybody, yeah, question?
So you wouldn't want us to like just zoom in to like the very base of it so you see more? You want us like just...
Well, that's basically what you're doing. If you run another graph without this series, our plot will scale these all up. And that's equivalent to zooming, isn't it? Yeah. You see what I'm saying? I mean, so, yeah. So, yeah, questions like this always come up. You know, when you present data presentation, by the way, there's a really good book on data presentation, and it's famous. The guy's name is Tufte. Have you heard of him? Tufte. There's a real art to presenting data so that it's meaningful for the reader. And the guy who has done a whole lot of work on this, his name is Tufte. He does workshops and he shows, and he's written a couple of really famous books that are extremely valuable, and they're artistic, they're beautiful. He shows you how to, there's a whole lot that goes into just presenting data, how to present data to make it meaningful and to have the highest impact on the user. On the reader, for the reader. Anyway, you might want to check that out sometime. Okay, any more questions about the paper? So when's it due? Tuesday? Is that right? Tuesday? Okay, well then there might be questions on Monday. So anyway, we'll forge ahead then. All right, so now the next data structure we're going to look at is our binary trees. So, in the same way that we had 3 different implementations of the list, the linked list, we are going to have 3 different implementations of the binary tree. Okay? So this is just to show you that the composite state pattern is not limited to lists, and the composite state visitor pattern is not just limited to the lists, but they are applicable in many different situations, many different scenarios. And here again, as we did before, the by tree L is the classic linked implementation, and this is the way it is usually done. But what's the second goal of the course? Learn object-oriented design patterns. So we're going to reinforce our understanding of the composite and state patterns, and then the composite state and visitor patterns in the by tree CSV. Yeah.
So you just said that the classic L is most commonly used for this. For the list, is also the L almost always used, or do they use that for?
No, it is the same for the list. Yeah, in both situations, the one that I'm giving you first is the linked is the one that's most common. Okay. Mm-hmm. But here again, you guys, here's what's going to happen. Now that we have like gotten over that hurdle of understanding how what the composite and the state pattern is and what the visitor pattern is, now the second time around things will really click more, and it won't be we won't have that hurdle, you see, because we've learned them now. And so now we're just going to so this is going to be reinforce what we already learned. So I think even though binary trees are like two-dimensional, you know, they have a left child and a right child, whereas a list is linear, I think this is going to be easier, actually. I think now that we've done a linked version, a composite state version, and a composite state visitor pattern version of the list, these are going to be, I think this is going to be easier, probably less time consuming for you to do. What is the mathematical or the formal definition of a binary tree? And the formal definition of a binary tree, it's recursive. An empty tree is a binary tree, so that's the base case. Yeah? The empty tree is a binary tree. And a non-empty binary tree has three parts. It has a left child, which is a binary tree, a data value of some type t, and a right child, which is a binary tree. Now, here's the thing.
What?
Okay, do you remember how whenever we did the linked version of the classic linked list without the composite state, and what were the two parts of a node?
Data.
Underscore data and underscore what?
Next.
Next. And what was next? Next was a what?
Pointer to a node.
A pointer to a node. Next was not a what?
List.
A list. Same thing.
Oh. Yes.
Are you with me?
Yes.
But now, here's the thing. Because binary trees are inherently recursive, what happens is the nodes are the ones. The nodes, many of the implementations for processing a binary tree are done by the nodes. Because once you get past the root of the tree and get into the nodes, then the nodes do the computation. You see what I'm saying? So anyway, we will see that that's how everything all pans out. All right, but I think it helps in the beginning to remember what the definition of a binary tree is, the mathematical definition. By the way, what's the mathematical definition of a list? Here, let's go back. What's the mathematical definition of a list? The formal definition of a list. What's the base case? An empty list is a list, and a non-empty list has what? Two parts. A first, which is an element, and rest, well, no, that mathematical definition, and rest, which is a what? Which is a list. See? So this is like that. This is similar to that, except instead of just having a rest, which is a list, we have a left subtree, which is a tree, and a right subtree, which is a binary tree. Oh, and by the way, the name of this project is BITREE, not B-tree. Notice that we've done this. It's bi-tree. And the reason it's bi-tree and not B-tree is because there's another data structure that we're going to study later on in the course, near the end. B-trees are different from binary trees. See? So that's why we stick this I in here. So that's not an accident. We didn't just, you could distinguish from B-trees. We're going to do B-trees as well. B-trees are not binary. Yeah, we'll see. Okay, so in figure 8.1 is an abstract binary tree. And so, the root is at, the top node is called the root, and then the 30 has a left child, and the left child has a root of 70, and it has a right child, and the right child has a root of 80. And each one of those is a binary tree. Okay, so this is the way it looks. This is the way a binary tree looks abstractly. It's an abstract binary tree. And now the question is, how are we going to program this up? Well, the linked version, here in part B of the figure, the linked version has, what is that little container at the top? It is a what to a what? It's a pointer to a node. It's a pointer to the root. So that's what defines a binary tree. Are you with me? So the binary tree consists of, so the attribute of a binary tree has one element, has one attribute. A binary tree has one attribute, and that attribute is a pointer to a node. And then, so the node is going to have 3 parts, you see. And so the left child, there's going to be a pointer to a node that's going to point to the root of the left child, and a pointer to the node that points to the right child, and et cetera, down and so on. And then the ones at the bottom that don't have any children, if a node doesn't have a left child or a right child, then that left child or that right child is the null pointer. So here we're back into pointers now with null pointers, all right? Okay, low level of abstraction. So that's the picture in part B, and then on the right-hand side of the diagram is the code for this. So let's take a look. You see the link up at the top is it's the class BI tree L, binary tree L. So the binary tree has a what? An underscore root, which is a what? L node T star. So that one at the top is underscore root, and that's a pointer to a node. Are you with me? And then you see now what are the attributes of, so here are going to be the attributes of a node. The attributes of a node is we have underscore left, which is a what? Pointer to node. Underscore data, which is of type what? Type T. And underscore right, which is a pointer to a node. Does everybody see how that works? So that's the code that corresponds to that. And this, and by the way, this is the way we're going to do it. Now, do you remember the variations that we had of linked lists? Remember we said, well, the easiest way to do it is just to have one link, just have 2 parts to the node, and it would have underscore data and an underscore next, and next is a pointer to a node, and that would have an underscore data and an underscore next, boom, boom. And we had all these different variations. What did we do when we had, what was one of those variations when you wanted to be able to move backward in the list? Remember what we did?
The doubly linked.
Doubly linked, so we had it pointing back. Now, what do you think? Which way can you go here? What direction can you go? What direction do you, when you follow the links, what direction can you go? As you can only go down. What if you want to be able to go up? Well, but what would you add?
A pointer to like a
To what? A point. You would add a pointer to what? To the parent. That would be the equivalent. That would be the equivalent to having a doubly linked list. So you can have like a quote doubly linked tree. You'd want to be able to go the other opposite direction. And so that's common, by the way. And so here in figure 8.1c is the picture. If you had the equivalent of a doubly linked list, this is like a quote doubly linked tree. Yeah. So not only would you have a left pointing to the left child and a right pointing to the right child, but you would also have a what? A parent that points up to a parent. Are you with me? So every node has 2 children, but also every node only has what? One parent. Are you with me on that? Okay, so here's the code for that. You would still, the underscore root is still a pointer to the root of the tree, but now each one of these nodes not only has an underscore left and an underscore data and an underscore right, but also has an underscore parent, and that's that top box that points up. So now, and this is common. In fact, we used to do just recently. We used to do it this way in this course. Turns out that you don't need to. The course has evolved, and we're doing things a little bit differently now, and we're not doing this doubly linked tree anymore. So what we're going to do in our project, in the List L project, it's going to be as in figure 8.1b. All right. So. But you should be aware that some algorithms call for this doubly linked binary tree. Okay, now in figure 8.2, these are all the methods that we're going to implement. Well, we're not going to implement them all, but But these are all the ones that would be possible to implement. So notice that the UML diagram, the class diagram on the left is by tree L. And what do we have for its attribute? Underscore root. And what does that hyphen mean in front?
It's private.
Private, okay. And what is it? What is its type? According to that UML notation, it's a pointer to an L node T, right? And then we have the constructors and the destructor. And now, so in alphabetic order, what do we have? We've got clear, contains, copy root. Oh, copy root, that sounds like what? Copy head, yeah. And then equals, that sounds like equals. Height, in order, insert root. Is empty, left is empty, max, num leaves, num nodes, operator gets. So there's the overloaded assignment operator. Post order, pre-order, rem leaves, rem root, right is empty, root, set left, set right, set root, and toStream. And now these are all methods of the list, and frequently there are identically named methods for the node, even though this is list L. And typically what happens is there's a special case if the tree is empty. So the way an algorithm works is it checks to see if underscore root is the null pointer, is nil. And if it is nil, then it does the special case. And otherwise, if it's not nil, it knows it's a pointer to a node. And then what it does is it calls the corresponding method for the node. And then the node methods they call themselves. The node method will never ever call a list method because this is not the composite pattern. Are you with me on that? Okay, so when you code this stuff up, just keep that in mind. That's the general pattern. That's the general idiom of how the code works for this linked binary tree. So, but have I been saying list all this whole time?
I think I've been thinking of like
Switching between the two? Yeah, okay, from now on do a textual substitution. List replaced by binary tree. So anyway, yeah, so your question, where were we?
Yeah, could you explain the general idiom thing again?
Again, yes. Now, yeah, and I'll say it with the word tree, binary tree. Okay, so the general pattern for programming these methods for this by tree L project is the binary tree has one attribute called underscore root. And what happens is it's usually a special case if the tree is empty. So then the method for the binary tree checks to see if the underscore root equals the null pointer, and if it is, it knows that the tree is empty and it handles that case. And if it's not, then it knows that it's a pointer to a node. So what it does in that case is it calls the corresponding method for a node. And then the node for the binary tree never calls the method for the binary tree. It always calls the method for the node. So the node methods can be recursive, and they frequently are because the definition of a tree it's a recursive definition. Do you see what I'm saying? So you'll never have the case like we will in when we do the composite state pattern. What'll happen is the left child will be a tree, and so you can call the tree version. But we can't do that here because this is not composite. Does everybody see the difference, the programming idiom there? Are we good? And then so for example the in order of the binary tree will do something if the tree is empty, but if it's not empty, then it will call the in order of the node, and then the in order of the node will call itself recursively the in order of the node. See? So that's generally the way, when you code this up, that's the pattern to look for. And look, we have there's no inheritance here, no abstract, no anything, no inheritance. What does that solid diamond represent? Not inheritance, but what's it called? Starts with a C. Uh-oh. No review of terminology here, UML terminology. What is that? The solid diamond is what? It's not. Okay. How about this? Is it Haza or Iza? It's Haza. So we know that. But what's it called?
Composition.
Yes, class composition. It's class composition. So a binary tree has a root, has a pointer to a root, but then, has a pointer to a node, and then, but then what does a node have? A node also has what? A pointer to a node. Okay, in fact, it has 2 pointers to a node. Left child and right child. Is everybody good? Okay, so those are all the methods. And now in figure 8.3 is a picture of the structure of a tree and a structure of a node in more detail. So you see, if that top box on the left in part A of figure 8.3 is my bi-tree, my binary tree, then the underscore root is my bi-tree dot underscore root. And that underscore root is a what? Pointer to a node. So that's a pointer to a node. So star my bi-tree dot underscore root is the thing to which my bi-tree dot underscore root points. Are you with me? And then dot, and then that dot underscore right. So what's the abbreviation for a star and a parentheses and a dot? That's the what symbol? That's the arrow. So my bi-tree dot underscore root arrow underscore right is that underscore right part of the node, and it itself is a what? Is it a binary tree? Yes or no?
Yes.
Is it a binary tree? Yes or no?
Yes.
No.
It's pointing to an L node.
No. Hold on. It's not. This is not the composite pattern. It's a pointer to a node. Yes.
The definition of binary tree says that the right child is a binary tree.
I know, but that is the mathematical definition. But this implementation does not match the mathematical definition.
Oh.
That's the point.
Okay. Well,
Are we? Yeah. Is everybody clear on this? Yeah. See, now, it's really important that we understand that we're not dealing with the composite pattern here. Yeah. So maybe it was misleading to show the mathematical definition of a binary tree and then show that. But the point is that that's a contrast, that's not what it is. Are you with me? So when we do the composite state pattern, then that part will be a binary tree. But here it's not. It's a pointer to a node. Is everybody clear on that? And then my bi-tree dot underscore root arrow data is the data part, and my bi-tree dot underscore root arrow left is the left part. And what is the left part? It is a what? Is it a binary tree, yes or no?
No.
No, it's a pointer to a node. But here in part B we're going to abbreviate it like this. Are we good? Is everybody clear? Now, let's do a demo. Okay, so here's our demo. And the name of the project is BiTreeL, so you'll need to install that. And here's the BiTreeL.hpp. Let's just go ahead and run this. See what happens. And I think we're going to need a little more room here. So let's move this up. Okay, so look at all these options we have. Root, set root, insert root, rem root, set left, set right, clone, clear, rem leaves, num nodes, num leaves, height, max, contains, equal, right, pre-order, in order, post order. And look, I ran out of letters. So pre-order, in order, and post order, XYZ. So anyway, it was a real struggle to figure out what letters to call each one of these things. You don't know how much agony that gave me. So anyway. So here we go. Now, first of all, let's see if we, and by the way, there's 0.4 binary trees. So now we're going to be able to combine trees. Yeah, so we have more than one, right? So we have 5 of them to work with. All right. Now, first of all, let's see what, they're initialized to the empty tree. So let's try to write, and let's write tree 0 and see what it looks like. Now, so does everybody see what an empty tree looks like? It's just a little star. Yeah, you'll see why in a minute. Okay. Now let's see what root does. Let's try root. Root value of which tree? Tree 0. Well, that tree is empty, so we can't do the root value. But what about set root? Do you think we can set root? Set root to what integer value? Let's say 30. Set the root of which tree? 0. Oh, can't do that either because the tree is empty. So what did we learn from this? Set root assumes that the root already has a value. Are you with me? Okay? Yeah, so that's what we need to do to get one started from scratch is we need to do insert root. Is everybody clear on that? So insert what integer value? 30. Insert into which tree? 0. Insert root into which tree? 0. And so now if we write tree 0, look what happens. Now do you see how that tree got printed out?
Oh God.
It's 30, and then it has an empty left child and empty right child. Are you with me? And now we can set the root of this. See, so if we do set root to what integer value? Let's make it 80.
So is that
And
right?
0, we'll see. Yeah, let's take a look. And let's write 0, and you see what it did. It overwrote it. So does everybody see what set root? It assumes that there's a root there, and it sets it. Is everybody clear on how that works?
What if you try to insert a root into a non-empty thing?
Yeah, oh, that's a good question. Let's try to insert root into a non-empty tree. Let's do I. Insert what integer value? Let's say 70. And let's do it into 0 and see what happens.
Okay.
I could have paid you to ask me that question. That was a good one. Does everybody see what happens? The tree must be empty to insert root. So we can't do anything with this tree. It only just has, how are we going to build a bigger, building bigger barns. How do we build bigger trees? We must do what? Combine, we have to have two trees to combine somehow. How do we make the tree grow?
Set left, set right. Oh wait, no.
No, I think you're right. I think you're right. Here, let's experiment. Let's insert what integer value? So we have 80. Let's do 20, and let's do that into 1. All right. So now if we write tree 0 and we write tree 1, whoops, and we write, oh, I hate it when that happens. Before that calamity happened a minute ago, let's insert into another tree. So let's insert. What was I going to insert?
20.
20. So let's insert 20 into tree 1. Are you with me? So if we write tree 0 and write tree 1, this is what tree 0 and tree 1 look like. Are you with me? Now, what do you suppose? How do we get it bigger? Set left and set right. So let's see how those work. So let's do F for set left. Set the left child of which tree? Let's set the left of tree 0. That's kind of like our base tree. Set the left child of which tree? 0. Set it to which tree? 1. And now let's write tree 0. And you see? Yeah, now here, that's a good point on this orientation. What you have to do is you have to cock your head left. Do you see what I mean?
Did it get rid of the 20 that was in?
And that's a good question. What happened to the 20? Let's investigate. Let's write tree 1. And what do you suppose is going to happen? It's Zippo. Okay. So what kind of a set left is this? Is this a copy set left or is it a cut set left? It's a cut set left. Yes?
So if you have a binary tree that only has a root, does that count as a leaf or not?
The root, if the root has no children, then yes, the root is a leaf. Yes. Okay, now does everybody see how this worked? So how would we get something on the right of 80? Well, let's insert root and let's say 50 and let's insert that into, let's reuse 1. So now if we write tree 0, it looks like this, and if we write tree 1, it looks like this. And now we can let's set right of the of tree 0. So let's do G. I was running out of letters. So G for set right, and set the right child of which tree? Tree 0. And set it to which tree? Tree 1. And now let's write tree 0, and what's it going to look like? And there it is. Is everybody clear? Okay? Yeah.
So you have to create a new binary tree if you want to add to.
Yes, yes. Yeah, the way you grow, this is the way you grow a tree. Right, these are going to be primitive operations in the visitor pattern. Yeah. Is everybody?
A binary tree that's more than just one element.
Well, we for sure have to be able to make it deeper than, you know. So here, let's explore that. Let's explore that. Let's clone. Let's clone which tree? Let's clone tree 0 and copy it into which tree? Tree 1. So now if we write 0, it's that tree, and if we write 1, it's that tree also. Now just to make things a little bit different, let's set the root. Let's set S for set root. Let's set the root, let's change it to like 90 of tree 1, just to make them different. And so now let's write tree 0 and write tree 1. Okay? And so now, now what do you suppose happens? Now what's going to happen if we do, now what should we change? Shall we change the left child of tree 0? Let's set the left child of tree 0 to tree 1. Are you with me?
How does it know which left child you want, though?
There is only one left child.
There's 2 left childs.
There's
No. Okay. Watch the prompt. Let's do F. Set the left child of which tree? Now that one at the top is, we're going to set the left child of the one that has the root 80, right?
Okay.
So we're going to set the left child of tree 0, and we're going to set it to which one? We're going to do 1. Now watch what happens. What do you suppose is going to happen to that 20 that was the left child?
It's going to be
Now the
90.
90 is going to be...
Okay, so now here let's write 0. All right, and now let's write tree 1. And see, it is a cut. Notice that it cut it. But what happened to that original left child of 80? It got cleared. Are you with me? It got cleared.
So...
Do you see? It clears it. Well, I mean, because if you're going to put it, you're going to be able to put it on the left. What happens to the original left? It's gone. Now, does everybody see how these methods work?
So if you want to have like
It's gone.
5 log, you have to make 1, and then make the second one, and then make the third one, and then...
Yeah. Yes. Yeah. But I mean, that, you know, trust me. What else? Yeah. Now, what we are going to see is, eventually, we are going to build a binary search tree in which we insert and keep it in order, right?
Yes.
You see, but these are not. By the way, these are not search trees.
Right.
Okay, these are not binary search trees. These are just binary trees. There's nothing about the order. Notice I can put any order. Okay, is everybody clear on that? Okay. Now tell me. Oh, by the way, you guys, what do you think it's like to write the output and have this tree look like this? Yeah, let's think of that's
not a homework.
Fortunately for you, that's not a homework assignment. Okay, yeah, that's done for you. Fortunately, I'll show you a little bit about how it works, but not much in a minute. Okay, but now here, what about these other ones? Like clear would be obvious. Clone we already demoed. Rem leaves. I don't want to remove the leaves yet. What do you suppose num nodes should be? How many nodes does this have?
5?
Yeah, I think that's right. I think it should be 5. So let's do U. Number of nodes for which tree? Tree 0. Yeah, so it's 5. So here, let's write 0 again. Okay, and how many leaves does it have?
3.
Which ones are the leaves?
20, 50, 50.
The 20 and the 50 and the 50, right? So that's A. G0. Number of leaves is 3. What about the height? Do you remember the height of a tree?
3.
I think it's 3. We'll show a picture of what the height means in a minute. So height 0. The height is 3. Let's write 0 again to get it in view. And one more thing. Do you remember pre-order, in-order, post-order?
Yes.
Well, we will review that in a minute here. Let's do pre-order. That's X. Pre-order of what tree? Tree 0. It's 80, 90, 20. Oh, shoot, we have two 50s. That makes it kind of hard to, but anyway. All right, so end of demo.
Or you could change the 50.
Yeah, well, we can't because the only thing we can do is set root.
Yeah, can't you create a new
Yeah, we could.
binary tree with like 30 in it? And
Oh, that's, okay, you want to do that? Okay, let's do that. So let's insert root, insert what integer value? 30, and we'll put it in tree 1. And so now if we write tree 0 and write tree 1, then we will set the right, now we want to set the right child of tree 0, correct? So G, tree 0, set it to which tree? 1. And so now if we write tree 0, it looks like this. And now what is the pre-order X?
80, 90, 20, 50, 30.
0. 80, 90, 20, 50, 30. All right. Okay, we're going to conclude this demo with a little screencast. I have prepared 2 more trees for us. Tree 0 has root 10 and left child 7 and right child 80. And tree number 1 has root 50, left child 40, and so on. So the next feature that we're going to demo here is max, M for max. So let's check the max of tree 0. So M, max of which tree? Tree 0. And sure enough, the max of tree 0 is 80. And here if we do max, maximum of which tree? 1. And sure enough, the maximum of tree 1 is 90. N is another one we didn't check before. So let's do contains, N for contains. So let's see if tree 1 contains 60. So N, search for which integer value? 60 in tree 1, and it looks like it's not there, and sure enough the tree does not contain 60. Let's write tree 1 again, get it in view, and now let's do again, let's do N for contains, and let's see if 30 is in tree 1, and sure enough the tree contains 30. Now let's write tree 0 again for this next one. Now one thing that is a kind of an important one that we failed to do in the lecture is rem root. So T here for rem root. All right. Now here is tree 1. This one is tree 0. So let's see what happens if we try to remove. It has a root of 10, a left child of 7, a right child of 80. Let's see what happens if we try to remove the root of tree 0. So let's do T for rem root. Remove the root of which tree? Let's try tree 0. Now watch what happens. The tree must have at least one empty child, because after all, if we remove the root 10, how would we know what to do with the 7 or the 80? It has 2 children, but if it only has 1 child, then we know what should happen. That 1 child should become the root of the new tree with the root removed. So let's write tree 1. And we notice that tree 1 only has an empty right child, but it only has 1 non-empty child, which is this one at 40. So now let's try to remove the root. So let's do T and remove the root from tree 1 and see what happens. And it returns the fact that 50 was removed. And now, sure enough, if we write tree 1, that the left child has become the new tree. So the 40 with the left child 90 and the right child 30. Okay, so that concludes this extended demo. Okay, so that was the demo. So now let's take a look at some code. First, we'll take a look at methods for output and characterization. And so here's the documentation. To-stream is what you would expect. A string representation is sent to OS, the output stream. Pre-order, in-order, and post-order, we demoed pre-order. And so that's the documentation for that. Is empty, post condition, true is returned if this tree is empty, otherwise false is returned. Oh, and I don't think we had, on the options, we didn't have test to see if left is empty or right is empty, but these are used by the other methods, okay? So left is empty, precondition, this tree is not empty, postcondition, true is returned if the left subtree is empty, otherwise false is returned, and similarly for right is empty. And then, did we query the root? I don't remember if we queried the root. We might not have in the demo. But anyway, you can ask what the root value is, and they'll tell you what the root value is. Okay, so that's precondition, this tree is not empty, postcondition, the root element of this tree is returned. And then num nodes, we did num nodes, num leaves, and height. Should have demoed max. That would have been a good one. But anyway, you know what it does. It goes through the tree and figures out the biggest one. Okay, so that's max. Contains would have been a good one too. Shoot, I missed a lot on the demo. Well, you can demo that. I think it's obvious what those things do. All right. Now, here's a little teaser for the streaming operator. So look, what happens is we overload the streaming operator, and all we do is call RHS.toStream. OS is the output stream. And what toStream does, now do you remember the first thing we said is what does the empty tree look like? So there's the code for the empty tree, OS star. But now here's the other thing. Else we do _root arrow toStream. And that _root, it takes 3 parameters. It takes a string, and another string, and another string, and OS. And the node implementation of toStream is not shown here. But if you're interested, I challenge you to understand that code, much less be able to write it.
That's great.
So you can look at that, because what has to happen, that you notice that, because it has to print it out one line at a time. One line, another line, another line, another line. So it has to know how many spaces over to do the vertical bar and the this. You see what I'm saying? That's complicated. You look at that. I challenge you to figure that out. Anyway, but fortunately you don't have to. So anyway, and see here, look here. So here's the way the 30, 70, 80, 90, 50, 40 tree would come out. So look, on the very top line it has the space, 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 and then hyphen, asterisk, and then blah, 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 hyphen. And those parameters, it's a recursive call, and those parameters with the strings are the strings that get passed, that get modified to put it in the right spacing. So anyway, I think it's pretty neat. So let's review our traversals. This is the definition of pre-order traversal. You visit the root, then you do a pre-order traversal of the left subtree if it is not empty, and then you do a pre-order traversal of the right subtree if it is not empty. So now, can we figure this out? What is the pre-order traversal of this tree? Anybody?
70.
Pre-order, not pre-order? I don't think it's 70.
30, 70, 90, 80, 50, 40?
I think so. 30, 70, 90, 80, 50, 40. Remember this? You guys have done this before. Right? Now, what's the definition of the in order?
Left, middle, right.
Well, what do you do first?
Is it
Left.
The root?
Left child.
Yeah, but the what of the left child? Would you do a what on the left child?
Pre-order traversal on the left.
Yes, you do. Well, no, it's in order.
Oh.
Are you with me? The definition of the in order traversal is you do an in order traversal of the left subtree if it is not empty, and then what? Visit the root, and then what? Do an in order if it's not. So what's the in order traversal of this tree?
70,
Now that's going to be what?
70, 90.
70, 90, correct.
30,
30,
50.
50, 80, 40. Is everybody clear? 70, 90, 30, 50, 80, 40.
How's that in order?
It's not binary search.
And it goes like left to middle, right, left, middle, right.
This is not a search tree.
Yeah.
So these are not in order.
No, I know they're not in numerical order, but it's just a lot of jumping around.
Yeah, well, that's what it is. And then post-order traversal is what? You do a post-order traversal of the left, do a that's hard to say fast. Do a post-order traversal of the right subtree if it is not empty, and then you visit the root. So now what's the post-order traversal of this? Now this is a little trickier. Oh, we have a little pause here, a little pregnant pause. Huh?
It's versus
Of
the
the left?
Yeah.
Do a post-order traversal of the left.
Why?
But then you do the post-order traversal of the 70, of the one that rooted at 70,
So 90.
recursively. So what is it? 90, 70.
30.
No, not 30.
Oh,
90, 70,
Not-
50, 40, 80.
90, 70.
80, 50,
No, not 80.
40, 80, 40.
50, 40, 80, 30.
yeah.
Right, okay, I think that's right. Okay, so now let's just take a look at the pre-order code. I'll show you the pre-order code, you have to do the other ones. So here's the code for the pre-order. Here's the code for the pre-order. Look, now you see what we said before, what the general rule is? You do for the tree itself, that's a special case. Are you with me? So what is the pre-order for the tree? If underscore root is not equal to the null pointer, then what? You do root. But now if it is equal to null pointer, then what? You don't do anything. So nothing comes out because the tree is empty. Are you with me? But then what happens is the pre-order of the node version calls the what? The pre-order of the node version. Do you see? So what is it? So the pre-order is you visit the root. So OS stream underscore data and then stream a space, right? But now we have to check to see if the left, you see that's a guard. We have to check to see if the left underscore left is the null pointer. So if it's the not pointer, we know that we know it points to a node, and we can do underscore left arrow, because if it were empty and we tried to do that, we'd get a null pointer reference. So everybody see? So when you code with pointers, you always, before you do a pointer, arrow, anything, make sure in your code that you know that it's not the null pointer. Guard it. Do you see? Are we getting this? And then, so if it's not the null pointer, left arrow pre-order, and then if it's the right is not null pointer, then right arrow pre-order. Yeah? Okay, good deal. See you Monday.